pH can have an effect in the solubility of salts, and sometimes changes in pH will affect how soluble or not soluble a particular ionic compound, a particular salt is. You have salts that are very soluble in water. For example, sodium chloride is extremely soluble in water and all sorts of proportions. You have other salts like, for example, barium sulfate that are very insoluble in water. So it's very difficult to dissolve in water. When you add a certain amount of barium sulfate, it has this formula, BaSO4, and you mix it with water, most of the barium sulfate will not dissolve, and only a small proportion will dissolve to liberate the ions of that ionic compound. In this case, the ions are the barium 2+ and the sulfate anion. And how much soluble an insoluble salt is given by what we call the solubility product, and we call it Ks. And if you think of a generic salt that has a composition AB with a certain AXBY, a certain number of atoms of A and a certain number of atoms of B, and let's say that A is the cation and B is going to be the anion, and it liberates the cations and the anions, then the solubility product for that salt will be the product of the two concentrations of the ions you have made to the power of the coefficients, how many of those ions you have made. So I've got here, for example, iron 2 hydroxide that liberates two ions, iron 2+ and two types of ions, iron 2+ and hydroxyl anions, two hydroxyl anions. The solubility product for that iron 2 hydroxide would be the concentration of the iron 2 ions and the concentration of the hydroxyl anions to the power of 2 from this coefficient. And this is a number that it can be measured experimentally. Again, it's affected by the temperature, and it happens to be 1.6 10 to the minus 14. A quick exercise to see just how comfortable you are with the concept of solubility products. These are three different insoluble salts that are all from barium 2. Barium fluoride, barium hydroxide, and barium sulfate. I'm giving you here the solubility products for these three salts. Could you order them in order of solubility from the more soluble one to the least soluble one? Using as a piece of information, I'm giving you those solubility products. Stop the video now, please. So how did you order them? Well, you need to remember that solubility product is the product of the anion times the product of the cation. So what does it mean to have a large solubility product? It means you have more of the anion and the cation. So the larger the solubility product, the more soluble that salt will be. It will still be insoluble because it has solubility product. It means not all the salt has dissolved, only a small proportion has dissolved. But within being insoluble, the order of solubility would be the most soluble one would be barium hydroxide, because it's the one that has the largest solubility product. The next one would be barium fluoride that has a smaller solubility product, 3 orders of magnitude, give or take, smaller. And finally, the most insoluble one, and it is quite insoluble, would be the barium sulfate. The three of them is the one that has the smallest solubility product, quite a few orders of magnitude different from the other two. So what is the effect of pH in solubility? Well, in general, when you have salts that are only slightly soluble, in general, when you lower the pH, when it becomes more acidic, they become more soluble. And that's a trick that is often used in metallurgy to separate, when you're separating the ore of a particular metal, it is quite common to use a strong acid to solubilize the metal as an ion, because in general a lower pH, a more acidic pH, will help insoluble salts become slightly more soluble. So acidic pHs can be used very effectively, for example, in metallurgical process to extract metals, but it can also be a problem, because low pH means that salts become more soluble. So that means that metal ions will get liberated from solid form into solution. So for example, when you have a low pH, you can solubilize metals that actually can be a problem for the environment: aluminium, lead, copper, cadmium, etc. So instead of being trapped in the as a mineral in the rock, in the soil, they get released into solution, into the environment. They get dissolved in water, and that is what happens when we are thinking of the problem of acid rain, of acid deposition. A more acidic pH means that metals, specifically aluminium, gets liberated, and it becomes available for the plants because it becomes dissolved in the water they uptake. And it is a problem because it limits growth on plants, and if ingested by animals, by organisms, it again limits growth and can affect reproduction and increase mortality. And the diagram I have here at the bottom, is just an example of the different species you can have of aluminium. So when you have aluminium in solution, depending on the pH, and here you've got from 2 to 10 specifically, you can have this aluminium, the metal aluminium 3, the ion aluminium 3 plus, in different forms, depending on how it reacts with water is dissolved. And the y-axis gives you this alpha between 0 and 1, and is that the proportion of aluminium dissolved, and in what form you're going to find it. So you can think of between 0 and 1, or if you prefer to think of percentages, between 0 and 100%. So what does this diagram tells us? It tells us that if you have low pHs, for example 2 or 3, then all the aluminium will be in solution in the form of this blue curve that is aluminium 3 plus, as the ion, the cation aluminium. When you move to higher pHs, this aluminium 3 plus starts being transformed into other species with the hydroxide anion. And finally, at some point, at a particular pH around between 6 and 7, it disappears, and you have all those species until you move up to pH 10, and you have the aluminium tetrahydroxide anion. And why do we care about this? Well, because those species have different toxicity levels. So at very low pHs, the most abundant compound, aluminium, is more soluble to start with. So it comes off the soil and into the water. And at low pHs, it's in the form of aluminium 3 plus, which is more toxic than some of the other species. So especially when you're looking at environmental issues, you can use pH quite effectively to predict what sort of species you're going to have in solution, for example, metal ions, and what form they are going to be, and then what toxicity that those different species might have, and how they affect organisms.